Hello and welcome to my paper presentation. My name is Bibrak Kamar Chandio and I am a PhD candidate at Indiana University Bloomington. My work deals with finding new architectures, programming model and runtime systems for dynamic graph processing, especially considering systems that are non-von Neumann and message driven. Today I'll be talking about some of my works, especially in this domain, using the continuum computer architecture as a driving vehicle of the exploration towards newer architectures, runtime systems, and programming models. If we look at the nature of graph processing, we find a large amount of latent parallelism, irregular memory accesses, and very fine-grained computations with varying latencies and low floating point to byte ratio. By latent parallelism, we mean that edges can represent the fine-grained parallelism which is inherent into the structure itself. It is there but needs to be explored at runtime and also using a programming model that can expose it to the user given the nature of the input data graph which is not known at the time of programming or the compilation. And finally, with fine-grained computations, we see that the graph operations themselves are inherently very low compute intensive as compared to the bytes that are being fetched. There is mostly maybe an update to a vertex, and then there is a indirect memory indirection, which means memory needs to be fetched or the operations need to be performed somewhere else. This is in contrast to the workloads that are mostly coarse grained, where there is opportunity to do SIMD computations or other forms of parallelism on the data before performing a synchronization step. In graph processing, we see that communication dominates and the communication itself could be very irregular as opposed to a more confined bulk synchronous form of communications. So we take the point of view in designing a newer system for graph processing to look at all the levels in which the graphs are represented. These can be the data graphs themselves. This is the input data as we talked about earlier given to the program. And then the input data itself is structured at runtime into a form of what's the data structure of the graph. Mostly these are the agency list, agency metrics represented as the CSR format or vertex objects using pointers. And using the data structure, a programmer would write a program which would define the data flow of the graph or the algorithm, and then the compiler would come in and maybe adopts it or changes it for more optimizations. And then at the runtime, when the program is executed, it creates what's called the execution graph. And finally, the execution graph ultimately runs on some architectural topology it could be a network on chip or system area network which would compose of their own routing algorithms. So we take a point of view that if we can look at all these layers instead of optimizing a single layer or maybe two, but take a holistic approach and see how a new experimental system could be designed such that it is from ground up conceived to be a graph processing system. With that in mind, the design goal is more of an architectural unification such that the primitives and semantics and memory model must manifest at all levels of the system, especially considering the three main components. One is having a global namespace. So instead of having a segregated view of data which is contained logically within processes and which are in turn physically separated by caches, NUMA domains, and nodes, we would want them to be represented in a single global namespace. And the communication model must also be united such that instead of having multiple communication models such as shared memory and message passing glued together, if we could represent a single communication model which doesn't stage the data into hierarchies and optimize for bandwidth, but rather for a large number of small messages, because graph processing workloads, as we themselves do not contain much coarser grain parallelism, but rather fine grain parallelism, which could be exposed and exploited later on using smaller messages which are spawned using the edges of the graph themselves. And finally, a programming model which is a departure from the conventional hybrid forms of parallelism to a more dynamic form of parallelism which spawns asynchronous parallel computations from where the data exists rather than where the processes exist and then the data is sent towards the process. We organize our memory-driven architecture as a collection of compute cells. These compute cells are capable of storing data, data manipulation, and data transmission to adjacent compute cells. Here is represented an abstract compute cell which has its own computing logic and some memory, and it's connected by a network on chip. In a more real setting, ultimately the actual shape and capabilities of a single compute cell along with how these cells are aggregated together to form a continuum computer architecture chip is a design compromise between three parameters, which is memory, compute, and communication. So in this representation, we can see that at the left extreme, we have an infinitesimally small compute cells where the memory with each cell is very limited and also the computing ability is very limited, but there are a large amount of such cells. And if we go to the right, we see that they get more capable and also increase their memory, but then there are a lesser amount of these compute cells. So there is this continuum from the very small to the very large, and the optimization space exists in between. Candidate shapes for the compute cells may be triangular, square, or hexagonal, varying in their amount of die area that they represent and also the resources that they occupy, with the triangular having lesser communication links as opposed to the hexagonal and occupying lesser amount on the die, but then increasing the latency when they are tessellated as such. In the scope of this paper, we only focus the middle ground, which is the square tessellated compute cell. And we try to see how many we can fit in a constant chip area. In this case, under 306 millimeter square implemented using 7 nanometer. Much of our models and details are in the paper, but we can see in this graph, as we increase the amount of memory on a single compute cell and then tessellate them all together, we find that we are able to fit lesser amount of compute cell, meaning that the amount of parallelism is lowered. We also see that when we have large amount of compute cells, especially when per compute cell memory is lower, the total chip memory is lesser than what it could be achieved when per compute cell memory is higher. So there is a play to, in this case, about 1 gigabytes of SRAM can be fit into under 306 millimeter square CCA chip. And we also find that as we increase the number of compute cells, the mesh network on chip diameter also increases, which means that there is compromise between all these values for a single chip design. Here we explore what can be called a diffusive programming model, in which asynchronous actions are sent from a memory locality to another target memory locality. So these memory localities will be the compute cell sending an action which contains some amount of work that needs to be performed at another compute cell. Essentially what we would do is that a vertex would send a message to another vertex along its edge. From the programmer's point of view, the programmer writes actions. In this case, BFS action breadth-first search is shown, where the first argument to the action is the memory address where the vertex exists. The action will go and be invoked over the memory location where the vertex exists. The action can have any amount of payload in the form of arguments. In this case, it's the level, which is an integer type. When the action is invoked, it performs some work, in this case updating the vertex level, and then it'll diffuse onto the receiving vertices edges. What it does is that it will go into the edge list of the receiving vertex and propagate the same BFS action with the newly updated level. In this case, what will happen is that the computation will be diffused along the vertices through their edges. But to initiate the diffusion itself, at least one action needs to be diffused first. So here we see a typical main which initializes the device and creates the graph structure on the device, and then seeks the root pointer for our BFS search. Once we have the root pointer, which is the root vertex, we create an action, which is the same action that we talked about, and we register that action and get the handle of that registered action, and also create a terminator which will detect when the computation finishes. And what we do is that we germinate a single action over this action that we just created. This action is germinated on the chip, and then the computation is executed. Once the computation finishes, we get to know using our terminator object. Here we see the breadth-first search executing on a CCA chip. This is derived from a simulation trace using the CCA simulator that we have written. It's high level enough to be programmed using diffusive programming model, and yet is low level enough to simulate individual message movements. These messages are include the actions that are being sent from a compute cell to another compute cell. And you can see in the simulation the activation record as the compute cells become active, and then they send these messages to remote compute cells. The simulator is available online on the GitHub repository. It is extendable and can be used to simulate and understand various CCA configuration and runtime behaviors. Finally, to implement dynamic graph processing for a message-driven system, we need to devise new dynamic graph data structures. Typically, a vertex-centric data structure includes the vertices ID, some vertex-centric data such as level in this case of BFS, and more importantly the edges, which are represented in some locally extendable structure such as a vector. Now the issue is that these edges cannot be extended beyond a single compute cell, which means that as the vertex will grow in its edges, the compute cell memory can be exhausted, and there is need to find a way in which a single vertex can be occupied on multiple compute cells. This is not only needed for memory capacity purposes, but also to exploit parallelism. If the vertex is distributed across multiple compute cells, its operations can be parallelized. When it comes to parallelizing a vertex, there is an issue of how to parallelize the out degree load and the in degree load. So the vertex centric data structure must accommodate both kind of workloads. To distribute the out degree load and increase the amount of parallelism for a single vertex operation, we create what we call a recursively parallel vertex object. It is created using a single root vertex having a chunk of edges present in the root vertex, and as the edges grow dynamically, it creates new ghost vertices where it puts some of the edges, and these ghost vertices, when they grow, they create more ghost vertices, creating this hierarchical tree structure. We experiment with two allocation methods. One is vicinity allocator, which tries to allocate these ghost objects close to each other, aiming to lower the latency of hopping from one ghost vertex object to another. And then the default is the random allocator, which distributes the ghost vertices randomly all across the chip. We find that the vicinity allocator performs better as it lowers the latency of intra-vertex operations. But it still does not parallelize the in-degree load. For that, please refer to our following paper that augments the recursively parallel vertex object using the concept of rhizome to horizontally divide the edge workload in a way that the in-degree load is also balanced and also the out-degree load is balanced both at the same time. Much of the details are present in this paper. Finally, using our non-von Neumann memory-centric architecture and the programming model and the dynamic data structure, we are able to implement streaming dynamic graph processing. The streaming dynamic graph processing we are able to implement is at the finer granularity of a single edge insertion which is sent through the I/O channel. In this simulation, we show that the I/O channels are capable of interfacing with the compute cells on the edges, and they send out these edges, the vertex edges, to these compute cells, which then route them to where they would be inserted. And when they are inserted, we are now able to create more actions at the receiving locality. So for example, think about a BFS algorithm already have found the BFS level, but when a new edge is inserted or a new vertex is inserted, now we need to find the BFS level again. But instead of doing it from scratch, we can just create an action which will then update the newly formed edge to the vertex which it's pointing to, thereby avoiding the execution of the algorithm from scratch. We can see as the new batch of edges come, they update the vertices, causing new actions to be created. We use the input data graphs from MIT's Graph Challenge. There are two kinds of dynamic input graph. One is the edge sampling, the other is snowball sampling. With edge sampling, you would sample or you will create the graph such that it is observed in nature. Like it will randomly insert edges in the graph. So we see uniform number of edges in each batch. But with snowball sampling, it is more like discovering the graph itself from some starting point. So this will be much like a BFS traversal. As it increases in its levels, the number of edges increase per batch increment. At runtime, we see that with edge sampling, the amount of time it takes for just the edge insertions remains constant. But when the edges are inserted along with BFS, the time varies, but then it slows down. And this is due to the fact that these edges are inserted randomly, and they randomly activate the vertices, causing a chaotic BFS activation. But whereas if we see the snowball sampling, which was already derived from much like a BFS search, its time increases as the number of edges are increased. So if you remember, with snowball sampling, the number of edges also increase per increment. We also do some activation calculation of the chip. As the edges are inserted, we see these sharp declines in the activation status of the chip as the batches are ingested and they exhaust out, and then a new batch is updated. For more details, please refer to our following paper, which contains much of how we implement our streaming dynamic graph processing, especially the use of futures to allocate new ghost vertex as a new edge is inserted in a vertex, and how this is achieved using the concept of continuations. Thank you very much.